Good evening. We would continue revising few of the concepts of Newtonian mechanics. In this particular video, we would be dealing with velocity, distance, speed, acceleration, momentum, impetus, and work done. These are the basic important concept of Newtonian mechanics. So we would be dealing with this. We would be avoiding calculus, both differential and integral, for this particular video, because we would just stick to the basics, algebraic formulas, graphs, and so on. That would give a clearer picture to the students as well as those who are starting to build up the concepts of physics. So these are the topics which we will be covering. Each of them are related to each other. As you can see, momentum, impetus, work done, those who have seen. We won't deal too much about momentum, but we will start with the basic part. We won't go too much into these mathematical calculations so that things becomes clearer for you. So just to start with the Newtonian mechanics with this concept, what we would do is that we will just quickly write over what is the formula that we initially started with. We started with the formula which we all know, that force equals to mass times acceleration, F equals to ma. Newton's third law of motion, however, says something like this. Let me just quickly draw a graph for you. So if this is something which is a wall, if I consider, and I am standing here and I am leaning on the wall, that means I'm exerting a force on the wall. That means if I am exerting a force on the wall is equally exerting a force on me. So if I write this myself as body 1 and I use body 2 as that of a wall, then what I can write is that the force exerted on body 1, that is FB1, will always be equal to force exerted by body 2, that is force on body 2, that is the wall. On the other way, if I want to draw another graph and just wanted to show that here I am standing and I am standing on the ground, on earth, and I am exerting a force on earth and the earth is also exerting an equal force on me. So that is why the force exerted on body 1 will be equal to the force exerted on body 2. Well, that is my phone ringing. You have to just give me a minute to do so. Right, so this is force of the body 1 and this is the force on body 2. Now we also need to understand that what is velocity. Now velocity, if we can just write it as well, velocity equals to distance by time. We know this. So velocity would be equal to distance by time. Now what are the units for that? Let us see what are the units for that. Distance, it would be, say for example, if I'm moving at a speed at a velocity of 60 miles, so it would be something like, it would be 60 miles. It would be 60 miles and time, say for example, it would be hour. So the units for the velocity will be 60 miles per hour. It would be 60 miles an hour. Now what is the difference between velocity and speed? Let us get that quickly corrected. Velocity, well, velocity, as we know, it is a vector quantity. So velocity, we write it as vector. Generally we denote a vector by an arrow sign on it, so we denote it as v arrow, right? This is a vector quantity, whereas on the other hand, speed is a scalar quantity, so we get speed is a scalar. The most unique way to understand what is a scalar is that you don't get a kind of any sign over it, so it denotes that it is velocity. This is a scalar quantity. So this is velocity which has got vector, that means it has got both magnitude and direction. Speed is a scalar quantity, which means it has just got magnitude and no direction. Now suppose for example, if we are starting at a point here, say for example u, and I'm moving at a certain velocity and I reach to a final destination which is v. Right, we started with u, we ended up with v. And what is the acceleration? What is the acceleration? So we denote it as a. Acceleration is v, that is the final where we reached, and minus the initial one, whole divided by time. So this is what we call it as an acceleration. So it is the final where we reached minus the initial, whole divided by time is the acceleration part. right? So from here what we can do is that we can quickly write over another important part, just crossing them over. What we can write over here is that AT equals to V minus U, right? And then we can write another thing, which is our first conclusion, I would say a first formula, which is most commonly used in physics, is that V equals to U plus AT. And this is our first important formula which has been widely used in physics. V equals to, that means velocity equals to what you start with plus you accelerate at a certain speed and then you multiply it by time. Let us look forward how this movement would look if we can plot it on a graph. So I will use a simple graph, something like this, right? And what we are doing over here is that we are mentioning the velocity over here. We started with an initial velocity u and we reached at a velocity of v, and the graph will look something like this, and we drop something over here. So what we get over here from this particular graph is something like this. Let us just quickly mention the convention. So we start, this is the origin, which is O. We started with U, right? We reached at V, and we did it with a time of t. Now if you want to calculate what is the speed, so we can drop something like this also, right? So we drop something like this. So speed, as we know, as we denote it by the sign S, the speed in general, it is a convention in physics that we denote it by S. So we can write it S equals to this part plus this part. So I can call this is a triangle and this is a parallelogram or a kind of rectangle, say for example. So we can write it from here. What we can do is that we can write it from here that S equals to ut. Why? Because the length and breadth, because we have to take the area, that is this part, which is the parallelogram. So we will write it as ut plus what is the area of a triangle? We know it is half base multiplied by height. This is a triangle. So let me now draw the line. You will understand this is a triangle. So it would be half of base, it would be half of base, which is V minus U, half base multiplied by height. What is this is the height. V minus U is the height. This is the height. And what is the base? This is the t. T is the base, right? So we get half V minus U divided by t. So this is the height, this is the base, whole divided by time, right? So we get it something which is similar to, now you see, if we already know that V minus U is AT. You see, this is in blue, V minus U by AT. So what I can do is that I can write, therefore, S equals to UT, I substitute this UT part, plus half of, this one is what? V minus U by T, this is A, right? So I substitute this entire part by A, right? V minus U by T is AT, this one. So V minus U by T, this part I am substituting by AT times T, right? And then we arrive at the third and the second and the most important formula, this would be something like this. So we get from here S equals to UT plus half of AT multiplied by T gives to AT squared. And this is yet another formula which we get. So you see, what is the distance covered? Distance covered is the initial position that we started with multiplied by time that we travel. This is the time we travel plus half of the acceleration A multiplied by time squared, right? Multiplied by time squared. So this is what we are getting over here. So now you see that what we did over here, just to summarize, is that we substituted this 8 v minus u by t, which is a, I just put over this v minus u to at, v minus u, yeah, this is at, right, at multiplied by t, so it gives you half of at squared. Now what I will do is that this value v equals to at, this one, this value v equals to at, what happens if we start squaring that? So let us see what it actually leads to. Definitely we are doing it for some purpose. So what it would lead to is that if I write over here that v square equals to u plus at whole squared, u plus at whole squared, right? So we square both the sides. We square both the sides. V square equals to u plus at whole square. So by using the formula of the normal a plus b whole squared formula, what we get from over here is v squared equals to so we open this one. So what we get is u squared plus a squared t squared, that is b squared, plus 2uat, plus 2uat. This is quite simple, right? So this, we just expanded those values. From here, what we can also write is that v squared equals to u squared plus 2a. Yeah, I put it outside and then I put a brace, and I can also write ut plus half of at squared plus of half of at squared. So this is one. So from here further, what we can write is that v square equals to u squared plus 2a. Now what is ut plus at? Ut plus at squared is basically s. So what I can do is that I can substitute s over here. Let me write a little bit bold so that you will understand it's a substitution, right? Now if I take this a out from this equation, what is a? A is acceleration. And what is acceleration? Acceleration is equal to force by mass, right? It follows from this equation, force equals to ma, right? So v square equal to as. So from here what we can further write is that v square equals to u squared plus 2, I substitute a f by m. So we get f by m times s. From here, if we can flip over and rearrange it, we will get v square minus u square equal to 2fs by m. From there further we get m equals to u square, m equals to, m times, yeah, it would m times v squared minus u squared equals to 2fs. We're just proceeding with the normal algebraic formulas, nothing difficult. From here what we can also write is that m by 2 multiplied by v squared minus u squared equals to fs. I am bringing this 2 down here, so it would be m by 2. Now you will see that we have arrived at the third and the most important formula in physics, which is most commonly used, and this is this one. So solving this, it would be half of mv squared minus half of mu squared equals to fs, and this is yet another important formula of physics. Half of mv squared minus half of mu squared, 1/2 of mu squared equals to fs. Now if you note closely, you will find this part, this first part is the kinetic energy that we ended with. So it is the kinetic energy that we ended with. This part is the kinetic energy that we started with. This part is the kinetic energy we started with. And this actually gives us the work done. So this gives us the work done. Now work done, as you see, it has got Fs. That means it has got force as a unit is Newton. And we have got S, that is time, the distance, it would be in terms of meter. So we give them a new name, both this, we give them a new name as joules. We give them a new name as joules. So work done is measured in terms of joules, which is Fs, right? So this is one part where we have come to the conclusion that how we can deduce, or we can find out something like the work done and what is the value, what are the values. Now we come to yet another important concept of physics, which is called momentum. Now, I won't be expanding too much about momentum because momentum has got elastic, inelastic, different types of part. So I will just try to mention the heading. So we will deal with a little bit with momentum. Now, momentum, as we know, it is given by the notation P equals to mv, where we denote momentum as P equals to m times v. This is mass, this is velocity. Right. Now, this mass is measured in terms of kilogram. This is the unit. Velocity is measured in terms of meters per second. Right. Now, what is the rate of change of momentum? What is the rate of change of momentum? So it would be definitely mv minus mu whole divided by t. This is the final, this is the initial. So final minus initial gives us the rate of change of momentum, and from here we can write m equals to v minus u whole divided by t. Now what is v minus u divided by t? We know v minus u divided by pt gives us acceleration. This gives us the acceleration. Now we know from the laws of momentum that momentum is always conserved. Momentum is always conserved. So in order to demonstrate that, what I will do is that I will just quickly draw two simple figures. This is a body, this is a body, and after collision they are sticking together. So this is where they are sticking together. And by the law of conservation of momentum, say let us see, we name this one as m1 moving at a velocity of v1. This is m2 moving at a velocity of v2. Once they collide with each other, m1 and m2 remains the same, but they meet at a new velocity, which is v3. By the law of conservation of momentum, the mass times velocity, which is coming from this particular formula, this one, P equals to mv. So m1 v1 plus of m2 v2 plus m2 v2 will always be equal to the new one, which is m1 plus m2 times the velocity. This is v3. So momentum is always conserved. That means that the momentum which is there, we started with the adding with the momentum which is on the next part, what we get is a new moment. It is equal to m1 plus m2 times v3, but this will always be equal because momentum is always conserved. Consider a case of firing a cannonball. So say for example, if this is a kind of a cannonball that I'm firing, and this has got a say for example of a mass m1, and this is moving at a velocity of v1, then what will happen is that this particular body, this cannon or the firing instrument, if it has got m2, it is going to recoil. It is going to recoil at a new velocity of v2. So if you're firing something in this direction, you get a thrust, you get a thud, and this is a recoil. Further to this, there are certain other concepts like elastic and inelastic collisions, where you can find out that whether the momentum is conserved or not. But that you can look into other videos. But when we are speaking of momentum, one concept which comes is that always momentum or the conservation of momentum in terms of kinetic energy is not always equal to. That means it is not always equal. Say for example, energy changes forms, but it is conserved. Energy changes forms, but it is conserved. Let us take an example. Say for example, you are standing here and you are about to jump to a pool, and this is the base, right? You will be jumping from here to here, right? This has got a height. Say for example h. Now what is happening is that, and also there is a gravitational acceleration which is g, which is downwards, right? So when you are you're jumping from here, say for example you started 1 2 3 4 5 6 7, and when you're just about to touch the ground or the swimming pool, hope that you don't touch the ground, because otherwise there will be great accident. So hope you're jumping to a swimming pool. The entire potential energy which is here, potential energy is given by height, so it is mgh. So the entire potential energy of yours This is mass, this is gravitational acceleration, this is the height h. So the entire your potential energy is going to get converted to what? To kinetic energy, which is half of mv squared, and which we find out in the previous equations, right? Which we have shown in the previous equation, this one. See, half of mv squared, right? So if your potential energy gets converted to your kinetic energy, that means that this potential energy mgh will always be equal to your kinetic energy, that is half mv squared. Here both the m's gets cancelled out, so what we get is g, gravitational acceleration times height, is equal to half of velocity squared. So here your entire potential energy just before touching the ground, gaining speed, is getting converted to kinetic energy, and because both of them will be equal, so that is how it comes to. We will deal with the last part of our video, where there is an important concept which we would just like to touch base. We won't deal much with that. That is called impulse. So let me just put the heading something like this. It is called impulse. Now impulse is force. Now impulse, let me first give you the mathematical part of impulse, what it is called. So we denote impulse something like this. We denote the formula, we call it as delta P. Delta, nothing, it is just a change, equals to force delta T. This is the formula for impulse. Now delta P is what? Let me write it for you. Delta P is change in momentum, not rate of change of momentum. It is this, the change of momentum. Is a change in momentum. You can call it as change in momentum. F is definitely the force that is applied upon, and delta T is the time lapsed. So we put it as time lapsed. So these are the connotations. These are something which is there. Now force is the rate of change of momentum. We have seen it earlier. So what we can write from there is that F equals to mv minus mu whole divided by t. This is the, yeah, so this is what we know. Now what is the change in momentum? This is the change in momentum, mv minus mu. This is what we called change in momentum. So if this is the change in momentum, what we can write is that mv minus mu equals to I, and this is the impulse I, right? And I is equals to force, obviously, multiplied by time. And force multiplied by time is what unit? Force gives us Newton, times gives us second. So the impulse unit will be Newton seconds. It would be Newton seconds, right? So let me just quickly demonstrate before we conclude the video part. Say for example, we have got a mass m1, so we will stick to the basics, like we won't go to mn or something like that. And here is a brick wall. Here is a brick wall. Obviously it's quite a solid brick wall, which is not moving against the force. So if this m1 body is moving at a velocity of v1 and it strikes the wall, what happens is that m1 remains at m1, but velocity becomes 0. Because why? Because you have come to a stop. It is a halt, right? It has come to a stop. And mu, that is also equals to 0, right? We're starting with v, when we are ending, it is 0. So from here what we can get is that I equals to mv minus what? Mu. We have seen in this equation, right? I equals to mv minus mu, this one. But mu is 0, so we will substitute, we will put 0, right? So what we get is mv. And what is mv? mv equals to force times time. So what we can write from here, therefore, what we can do is that we can write ft, this is small t minded, the ft equals to m times v. ft equals to m times v, therefore f equals to mv by t. This is what we have deduced. So mind it that when you are traveling by a car, this car hits this wall. if your time, this t, is little bit longer, that means the time or the time that the car takes to hit the wall, if it is a longer one, then you're safe. That means the impulse, that is the force, will come down. I have shown it in my another video, what is the relation between the car safety, etc. So, and if this time, we can extend this time longer and longer, the force will come down because of the inverse square law, right? And that means that you are safe. If the time is less and the impulse is more, that means you are unsafe. That means you are much more prone to accidents, etc. So this is the concept of impulse. This is the concept of momentum, where we have seen the law of conservation of momentum. This is how we have arrived through different calculations. We have arrived to work done, how we can deduce it. This is what we started with, that is force equals to mass time acceleration, how we started deducing the values, and we calculated how we can calculate the distance, that is the calculation of the distance from this rectangle and this part. So that brings us to the end of the video. It was a longer one. I hope you liked it. We have almost covered all the concepts of Newtonian mechanics. We have covered velocity, distance, speed, acceleration, momentum, impetus, and work done. So overall, this has been my effort to show you. We started in here and we end in here. So F equals to ma, and we have covered these topics of Newtonian mechanics. If you have any comments, any suggestions, please do let me know in the comment box. Stay safe, stay happy, and look out for more videos which will be coming up on Newtonian mechanics and other geometry and related topics. Thank you very much for watching. Have a nice day and stay safe.